All right, hi everyone. Let's get started with our video lecture. There's a reason I'm having you do this at home, by the way, and it's because there's a lot of setup that I think you could just watch, but I think the value comes from talking it out in class. So you're gonna watch this, and then we'll talk about it in class as a collective. To start, I'm gonna ask y'all a question, and I think I've mentioned this before. So my favorite questions are the ones that look very simple and are actually very complex. For example, if I asked you for the sine of 75 degrees, what would you tell me? Right? I don't know that I expect an exact answer from you. I think you should definitely be able to tell me that it's somewhere between root 3/2 and 1. I think that would make sense. 75 being between, that's the other way for you, between 60 degrees and 90 degrees. But what's the exact answer for that? You know, very simple question in the way it's written, complex in the answer. I'm going to point out something, by the way, which we'll use later on. But 75 degrees, I hope it isn't too mind-blowing to say, is the sum of 45 degrees and 30 degrees. And so while we can't just add up the sine of 45 and the sine of 30, it's not really how the unit circle works. Maybe there's something we could do with 45 and 30 because we definitely know what the sines of those angles are and the cosines and the tangents and et cetera, et cetera. Right. So the question is, what can we do with that 45 and that 30? Well, to do that, we're going to construct the unit circle and do a little bit with that. I'm just going to draw a circle, and I'm going to make this circle literally as big as the screen allows me to make it. There we go. Actually shift that down so a little high for me. Is that lined up right? All right, there we go. Cool. Let me throw some axes on this. All right, and let's say, like we said, we were looking for a sine of 75 degrees, thereabout being 75. That feels about right. Yeah. Right, so all I'm doing right now is drawing in the angle that we originally wanted and splitting it into two other angles. Right, so part plus part would equal the whole. Now at this point, just so that we can make this more generalizable, because I might not ask you all the time for sine of 75, I could ask you for sine of, let's see, 125 or 175 or things of that nature, right? Let's make this more generalizable by assigning some names to our angles. Just say alpha and beta, right? Nice and general, and we can make them more specific later. Right, we're going to continue our construction by extend this and drop in altitude from this point of intersection on the unit circle down to the radius for our angle alpha, right? So this is just an altitude from a point to a line. Right, and then around that, we can construct a rectangle. So I'm going to put this over here, and I want this rectangle to inscribe this triangle that we've just created. Right, so to recap where we've been so far, we had our larger angle that was split into two smaller angles. We dropped an altitude from a point to a line, and then we constructed a rectangle to inscribe this triangle. Now I'm going to take a minute and just color code some things. So let's see if that'll, yeah, there we go. Okay. Put that there, put that here, put that there. Style, I do want it to fill in. That'll be our orange in the center. Duplicado. that here, drop that there. I'm just going to go in chromatic order here. Fill that up to yellow. Green. That's what I mean. Come on. Oh, good enough. And we'll call this one. All right, so now again, we were looking for the sine of some unknown angle, right? We found the angle in the unit circle. If we want the sine, we would just want the y coordinate of this point, right? Where the radius hits the unit circle. Which, looking at this rectangle, I think seems pretty clear. This would be the y coordinate of this point, right? Because it's just, you know, you drop an altitude to the y-axis, this would be the length from the origin. So I think we're pretty safe to call this sine of alpha plus beta. Right? Similarly, and we'll get to this later on, but if I wanted the cosine of alpha plus beta, right, and this is where the radius hit the unit circle, I would think that this segment also works for the x coordinate. I think it would be good to call this cosine of alpha plus beta. Right? The question is, can we find the other lengths in this rectangle such that it'll tell us more about sine of alpha plus beta or cosine of alpha plus beta? Right? Well, let's investigate. There's one length that I know for sure, and that's that this radius has to have a length of 1, right? Because we're in the unit circle. Everything else, I think, is a little more unknown, but not unknowable. Right, so let's go ahead and start labeling some stuff. I'm just going to call segments as I see them. Or you know what? Let's use points. I think points might be more beneficial. We'll say that's point A, point B. We've got C, D, E, and then F. Right, so 6 points around the rectangle. So if I wanted to find the length of this segment, let's say AC, then I could just focus on this orange triangle and use SOHCAHTOA, right? We already have an angle beta. We're looking for the adjacent side, and we know the hypotenuse. Sounds like cosine to me, right? SOHCAHTOA, cosine is adjacent over hypotenuse. So in this instance, and I can do this over here, the cosine of our angle beta, right? Again, if we're doing this geometrically for the orange triangle, SOHCAHTOA, would have to be the adjacent side, AC, over the hypotenuse, which was 1. Right, and looking at this equation, I would hope that it's pretty clear. Like this side length is just cosine beta. Right, so we can label it as such. This is, we can now call this cosine beta. Right, and if we did a similar thing for the side length EC, right, this segment right here, we did SOHCAHTOA again. This would be the opposite side from beta. So sine is opposite over hypotenuse, meaning that sine beta has to equal the length EC over the hypotenuse 1, right? Or similarly, this side length is just sine beta. Right? We can keep it going with our yellow and green triangles. So I'm going to zoom in down here. If I wanted the length AB, and I already know the angle alpha, right? Then this is cosine again, because AB is the adjacent side to our angle alpha. So cosine of alpha is equal to the adjacent side length, right, over the hypotenuse. We just found that the hypotenuse had a length of cosine beta. Right, you multiply it out, and you're going to find that the length AB equals cosine alpha times cosine beta. Right, we can do a similar thing over here. If I want to know CB, then that would be, as we've seen before, sine for the opposite side from the angle. Sine alpha is equal to the opposite over the hypotenuse, or sine alpha cosine beta is equal to the side length CB. We've got one more here. I want to know DC. I might use some SOHCAHTOA. The question is, which angle am I going to use, right? Well, we've already seen that we know alpha and beta, right? We have a bunch of right angles in the corners because of our rectangle. We know this is the right angle because we dropped an altitude, right? That actually helps us find more angles for that green triangle. So for example, in this yellow triangle, right, we know that all of the interior angles need to sum to 180 degrees. So this plus that equals 180. Or if we subtract off this right angle with 90 degrees, then this angle BCA plus this angle alpha have to sum to 90, right? That would mean that this angle must have a measure of 90 minus alpha, right? And if we take it back to some more fundamental geometry, this straight angle, right here needs to sum to 180 degrees. We know that this is 90 minus alpha. We know that this is 90, right? The only way that this works is if this angle right here is also equal to alpha. Right, so that takes us back to our side length DC. If I want to know DC, well, now I can see that DC is the adjacent side to this angle alpha, meaning we can set up with cosine. So cosine of alpha is equal to the adjacent side DC over the hypotenuse, which we said was sine beta, right? Or cosine alpha sine beta is equal to DC. Right, if we want to find the side length ED, this is now the opposite side from alpha. Sine alpha is equal to the opposite over the hypotenuse. We're going to multiply sine alpha, sine beta is equal to ED. Right, so to recap all that from the beginning, we had a sine of an unknown angle that we could break into more knowable angles, right? So we constructed that larger angle, we split it into two smaller angles, we dropped an altitude from this point of intersection on the unit circle to this radius, we constructed a rectangle around our triangle, and then knowing what we know about the unit circle, SOHCAHTOA, just some geometric principles, we were able to get all of these angles and all of these side lengths. Like I said, simple setup, complex work through, right? But maybe a little too complex. Let's strip it down just to the parts that we need. I'm going to come on down here. I'm going to sort of recreate that rectangle, and then we can throw some points down. We had a point about here and about there, right, where we had A, B, C, D, E, F, right? And we're looking at that angle, right, where the unit circle was arced somewhere over here. And if I were just to pull all of those lengths from that upper diagram down to here, what we had found, right, was that we had sine of alpha plus beta, cosine of alpha plus beta. Right, this AB, I'm just going to peek at that. AB we said was cosine alpha, cosine beta. Cool. Cosine alpha, cosine beta. ED Actually, remember we said was sine alpha, sine beta. And then CB, I have to peek at. Sine alpha, cosine beta. And then this would have been cosine alpha, sine beta. Right, and you'll notice that we now pretty much have all of the side lengths around the perimeter of our rectangle. Right? The reason that this is nice is because if we wanted to know sine of alpha plus beta, right, that was our original question. Well, in a rectangle, the opposite sides need to be congruent, right? Meaning that the sum of these side lengths has to be equal to this side length, right? Or another way to say that is sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. Right, just adding these two side lengths together will get us this sine value. Right, and this I think works for what our original problem was. Right, we wanted to know the sine of some angle that we could have broken down into smaller angles. Right, and this will let us just evaluate all of those angles and just put them together in a formula. Right, the sum formula for sine. Et voila. I'm also going to get you the cosine angle, the cosine formula right quick, and then we'll use that to actually answer our original question. So I'll just drop that over here. If we do the same thing, we're going to find with these two opposite sides of our rectangle that cosine alpha, cosine beta must equal the sum of cosine alpha plus beta, right, plus sine alpha, sine beta. This is not really how we present the formula normally. Normally, we'll just get this by itself by subtracting this product over with the other term. So the end result of that would have been cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. All right, so let's finally finish that actual initial question, which, as you recall, was the sine of 75 degrees. Right? We said that we could break that up into the sine of 45 degrees plus 30 degrees. Right? And if we use this formula, that would be equivalent, right? If 45 is alpha and 30 is beta in our formula over here, then we could say sine of 45 degrees times the cosine of 30 degrees plus the cosine of alpha 45 degrees times the sine of 30 degrees. Right, we're just assigning 45 to equal alpha, 30 to equal beta, and then plugging straight into our formula. Right, sine of 45 would be root 2 over 2. Cosine of 30 would be root 3 over 2. Cosine of 45 would be root 2 over 2 as well. Sine of 30 would be 1/2. Make sure you follow the order of operations. Please don't be the person who gets through all the hard bit of the formula and then doesn't like follow the order of operations. That'd be, a fumble at the 10-yard line. You'd hate to see it. Just follow the order of operations. It'd be root 6 over 4. And then we're going to multiply these two terms together. Again, PEMDAS. Root 2 over 4. And then final answer, root 6 plus root 2 over 4. Right, now, 2 notes about this. One, I think the most like pressing question for a lot of you is going to be like, oh my God, do I have to do all of this all the time just to get here? No, right? These formulas, you'll notice I just picked up back at sine of 75 degrees and jumped straight into the formula. Like these things, these formulas, we're going to treat as, you know, just known facts that you can just throw in whenever it's relevant for you to do the cosine of some sum of angles. Like you can just jump straight to this, right? You would just have to know what the formula is and how to use it. You do not need to derive it every single time. The other thing I'm going to point out about this answer is that you will see there often are a lot of root 6s and root 2s and 4s floating around. That does not mean that you will always have the same answer every time. The order could change, the signs could change, these numbers could show up in different places. It's a bit of a motif. You will see the 3 numbers a lot, but the actual answers themselves as to how you assemble, that will change. So just be on the lookout. Don't always give the same answer every time. All right, let's also talk about what happens if I wanted to, let's say, have the difference of an angle, right? Let's say I wanted sine of alpha minus beta, right? Well, we've seen already how the sine of negative theta is equal to negative sine theta, right? Or if that doesn't quite ring a bell, we could just draw something really quick, right? If I, let's say, had an angle here, right, with the sine value being the y coordinate, as soon as you draw the negative angle, right, your y coordinate is just going to be the same side length, but on the opposite side of the axis, right, or the negative of this y, right? So sine of negative theta equals negative sine theta. With the same drawing, you can see how cosine of negative theta would just be the same as cosine theta, right? The cosine of the positive angle ends at the same x coordinate as the negative angle. And then if those two things are true, then tangent of negative theta must equal negative tangent of theta, right? Because this, via substitution, would just be the negative sine theta over cosine theta. So negative divided by positive, give you this negative, right? Negative tangent theta. Right? We call those the even and odd identities. And if we were going to use that, right, in our sum and difference business, I think that can become helpful for us to write sine of alpha plus the negative beta, right? Alpha minus beta, that has to equal alpha plus the negative of beta, right? So then we can set up our formula, sine alpha cosine, this time we're using the negative of beta. Move these over to the right. And then we would add cosine alpha and the sine of negative beta, right? Well, for cosine of negative beta, we've seen how the cosine of a negative angle is the same as the cosine of the positive angle. So this we could just replace with cosine beta, right? There really wouldn't be any change there. This sine of negative beta, we've seen will have the negative of the sine of the positive angle, right? Or just negative sine of beta. Right, everything else can stay the same. This is a bit of a wonky way to write this. I think I would just take the negative out front. So instead of, you know, adding a positive times a negative, let's just subtract the negative. Subtract the negative, subtract the positive. I don't know, man. I think you get what I mean. We're just taking this negative out front. Right. And this is now our formula for the difference of angles, right, for sine. Sine alpha minus beta is equal to sine alpha cosine beta minus cosine alpha sine beta. I am just going to show you real quick how we actually put those two formulas together, both sum and difference, because we have the difference formula. The sum formula, we said, is this. You might notice that they're like exactly the same, except for one is subtraction, one is addition, the other has subtraction, this is addition, right? So we just represent this all together in one formula by writing sine of alpha plus minus beta, right, is equal to sine alpha cosine beta plus minus cosine alpha sine beta. Right? And that just gives us an all-in-one formula for sum or difference. We don't have to memorize two different things. Right? Similarly, we've said how cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. If we did the same thing where we said cosine of alpha minus beta, I should clarify these are separate things now, right? And then we said cosine of alpha plus the negative of beta. I'm just going to start to do this one a little more quickly because I just want to sort of show you the 2-in-1 formula. This would be cosine alpha. Cosine of a negative angle is just the cosine of the positive. We'd have minus sine alpha. This would have to be negative sine beta by our even odd identities. I've got a negative times a negative, so that would just be positive. Right, and this becomes our simplified formula for the difference of cosine. Okay. We can compare that to the original sum formula that we had. Right, and notice these are also pretty much exactly the same. You've got cosine alpha, cosine beta, sine alpha, sine beta. The difference, again, is the signage. But unlike the sum and difference for sine, we're using opposite signs for cosine, right? SIGN signs, opposite signs. So alpha minus beta results in a sum of these products. Alpha plus beta will call for a difference in products, right? So the way that we're going to represent that, cosine of alpha plus minus beta is equal to cosine alpha cosine beta minus plus sine alpha sine beta. Right? This symbol on its own, yeah, functionally is plus minus, like there's really not a reason to flip them. But we use this symbol in conjunction with a different plus minus to signify, like when you are using a plus here, right, the symbol on top of the plus minus, you should be using subtraction here, again, the symbol on top of the minus plus, right? So the symbol on top corresponds over here, and similarly, whatever symbol, if you use, subtraction here on bottom, you're going to use this plus on bottom over on this side of the formula. Right, so these are the two formulas, the two, 2-in-1 formulas. If you're going to memorize something, you got to memorize these. All right, we've got one more chapter to the story, and that would be the tangent of alpha plus beta, right? Not particularly worried about, secant, cosecant. Once we get tangent, cotangent, we'll just take the reciprocal after we evaluate with our formulas. But tangent, I mean, I think me personally, I think it'd be a mess to, do 4 different things and try to do like fractions over this and that and simplify all of it. Like we can get the simplification out of the way first, and we can make a nice, a much nicer formula for the tangent of a sum of angles, right? So let's see how that works. I'm just gonna start right down here. Right, the following have to be equivalent. We're going to start with the expression that we want, which is tangent of alpha plus beta, and let's just see where that takes us. Right, so tangent of alpha plus beta. Right, well, tangent as a quotient is sine over cosine. So I could rewrite this expression like so. Right, we just found our formulas for sine of alpha plus beta and cosine of alpha plus beta. I happen to know them off my head because, you know, I'm a professional. You just, you know, look above at the notes. I'll also say, like, the first time you're doing this, I think it's helpful to just have the formulas nearby, and eventually you can take off the training wheels and, you know, put them away and try to do the problems without directly straight at the formula. I mean, when it's brand spanking new, yeah, look at the formula. But sine of alpha plus beta, that's gonna be sine alpha cosine beta plus cosine alpha sine beta, right? Cosine of alpha plus beta, we can replace that with cosine alpha cosine beta minus sine alpha sine beta. Did my screen freeze? Oh, you hate to see it. Haven't done this in like a year since I was teaching on Zoom. Okay, I'm gonna, hold on. We're gonna end the screen share. See, it's been so long, I don't even know how to end the screen share. It's been forever. Oh my God. I hope we don't have to do this remote. This would just be awful. Okay. So now that's done. And then we're gonna reconnect. Hey, there we go. All right. So being back up on that. Cosine of alpha plus beta, once we use our formula, cosine alpha cosine beta minus sine alpha sine beta. Right, again, I know that because I'm a professional. You can just look at the formulas that you probably have written down somewhere. Or not. Would you be taking notes on this? No, you're probably just watching it. Take my word for it. Okay. So this, just awful to look at, just an absolute mess. Like, why would anyone ever want to use this? Too much going on here. Yeah, just way too much. Let's make it simpler by making it just a little more complex. I am going to multiply by 1. And you're like, what does that do? That doesn't do anything, right? And you're right. If we just multiply it by the actual number 1, nothing would change, right? But we could rewrite 1 as some fraction that would be equal to 1, and maybe that would be helpful, right? I'm looking here and I'm seeing sines and cosines, and they're just all different functions, and it's all over the place. Not a fan. If we were to multiply, let's say, the numerator by 1 over cosine alpha cosine beta, right, and we distributed this onto both of these terms, right, wherever we had a sine alpha, we'd end up with a sine alpha over cosine alpha. That would have to reduce to tangent. We'd have a cosine beta over a cosine beta, right? That would just have to straight reduce out, right? We can tighten this up just by multiplying in this fraction. And if we do that in the numerator, then we'll have to do it in the denominator. Otherwise, we're changing the value of the fraction. That's a no-no, not going to work, right? So let's do this. We're going to multiply this in, and that will get distributed onto all of our terms. Let's get this going. Put that there, put this up here. Right, this is getting distributed onto everything. Right, again, even more complex than the previous step, but things are about to get nicer. Cosine beta and cosine beta, bam, bam, reduce. Cosine alpha, bam, bam, reduce. What else we got? We've got cosine alpha, cosine beta, bang, 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 right? All of them gone. And so the nicer version, nicer quote, ends up being sine alpha over cosine alpha plus sine beta over cosine beta. This whole fraction reduced out. This is now just a 1 minus sine alpha sine beta over cosine alpha cosine beta. Right. Or this is just tangent of alpha. This would be tangent of beta. We just have our 1 minus. And then sine alpha over cosine alpha would be tangent of alpha, like we just saw. We also have tangent beta. So this would be the product tangent alpha, tangent beta. Right, and as we zoom out, we said that we would start here and move our way down, right? If each individual step, right, each individual expression is equal to the expression immediately after it, then by the transitive property, this tangent at the beginning has to equal this fraction at the end, right? And that gives us our identity. Tangent of alpha plus beta is equal to this fraction. Right? And if we use our even and odd identities, we'll end up with this more complete formula. Right, so tangent of alpha plus beta, tangent of alpha plus minus beta is equal to tangent alpha plus minus tangent beta over 1 minus plus tangent alpha tangent beta. Right, so that is our third sum difference formula. All right, at this point, I'm thinking that let's just do like 1 or 2 practice problems with it. I'm actually going to look for some inspiration off my old notes. Give me a moment. We already did 1 for sine because we did the sine of 75 degrees. I'm thinking let's do 1 for cosine, 1 for tangent. Could be good. Where did I put these? Okay. We're going to do cosine of 285 degrees. And then let's do tangent of 165 degrees. Cool. All right. Now, there are multiple ways to create these angles, like in terms of what numbers you're actually adding and subtracting. My tip for you is always look for the 45s. So, for example, I could represent this as cosine of, let's say, 120 degrees, and that would be what? 165? Right, like this would work, and this kind of doesn't. Right, so if you're always hunting for like pairs of angles, you know, you may spend more time doing that than you actually want to. So again, just look for the 45s. In this case, we could call this cosine of, I don't know why I'm starting with the 240, 45 degrees plus 240 degrees, right? Both of which we absolutely know how to work with. You could also, just for flavor, cosine of, what would be 330 minus 45. Right. Either way works. I'm actually going to do the difference just for flavor. Just, I think we did one formula with the positive, with the sum of angles. Let's do one with the difference. So based on our formula, we would have cosine, I'm just going to label these here, alpha and beta of alpha, cosine beta. We have a difference of angles. We're subtracting here, which means that we'll need to add here. Sine alpha, sine beta. Cosine of 330 would be root 3 over 2, root 2 over 2, negative 1/2, and root 2 over 2. And this is what I'm talking about. The root 6s, oh, sorry, that's a 4. And the root 2s and the 4s, they'll keep showing up, but the order will change and the signage will change, S-I-G-N sign. And so be on the lookout. Let's do one more. Let's do tangent. Right, and like I said, be on the lookout for the 45s. If I just take the 45 first, usually like 9 times out of 10, that'll get you to where you want to be. Maybe 10 times out of 10. Might be 10 times out of 10. So I break this up and I just say, okay, I'm going to start with 45 and add on some number. Yeah, I definitely can evaluate tangent of 120. Right, so knowing the formula, this would have to be, and again, I'll label this if it benefits us, alpha and beta. Tangent of alpha plus tangent of beta over 1, and this time minus tangent alpha, tangent beta. Right, now I definitely know tangent of 45 degrees, that's just 1, right? Because remember that your 45 degrees is on that y equals x diagonal. Tangent of 120, if you don't know off the top of your head, I mean, tangent, I think it's fine if you don't know off the top of your head, because you should be able to quickly pull it back. But 120 would be here with the ordered pair, negative 1/2, comma root 3 over 2. Tangent is y over x. So we're looking at root 3 over 2 over negative 1 over 2. If we reduce out the over 2s, right, you'll just get negative root 3. So 1 plus negative root 3 over 1 minus 1 times negative root 3. Right? Or 1 minus root 3 over 1 plus root 3. All right, so that basically wraps up the fundamentals of the sum and difference formula. Again, I am showing you this construction so that you have an appreciation of how to like actually prove things. You have an appreciation of where the formula comes from. I am not expecting you to do something like this, regularly moving forward. Just, know where it comes from, know your formulas, know how to apply them, right? If I throw a sine of 75 degrees or a cosine of 235 degrees, right? Things that, you'd have to break up into smaller angles. You just got to know how to use the formula to solve that, right? And that's going to be sine of alpha plus beta and cosine of alpha plus beta, right? And tangent of alpha plus beta. You got to know all 3.